Okay, guys, let's start to our real course now. In the week number 3, we have met at Hacettepe campus in the last, let's say, before the coronavirus outbreak here, vacation or break to the school education. Now we are resuming it. Resuming means we have 2 weeks past. Now we are in the 6th week. So I will go over slide week number 4, slide week number 5, if possible. If we are not bored, we will continue slide week number 6. In the previous 3 weeks, we have accomplished basic medical imaging or any imaging system properties. I gave 2 homeworks. You were required to obtain line spread function and modulation transfer function of your digital camera, and you have already uploaded it to OGR. I have not checked MTF homeworks, but I will give a feedback. Probably supply good homeworks for others' corrections, and they will not be graded. The grading issue is indeterminate yet, but I will tell in the near future. Now let's continue week number 4, which is right after the X-ray systems. X-rays, you remember we have learned X-ray photons, energies, and their imaging characteristics, generating of X-rays, X-ray imaging systems, and their basic definitions of system contents. Now we are continuing with the detectors. In the last, week number 3, we have considered the tube and X-ray tissue and matter interaction mostly. Now we come to the end portion of it, which is detecting X-rays. They are accomplished by so-called detectors. All imaging systems, detecting is the first step of the imaging. In today's, this is like samples of various X-ray systems which can be seen or observed or utilized in clinical environment. This one is mammography. Mammography is specifically for breast imaging, and due to very soft and delicate tissue nature, the energy of the X-ray is low. You see with the red line under the graph, diagnostic range of mammography is somewhat 7 or 8 kiloelectron up to 20 kiloelectron, which is really low because the tissue is very thin and the contrast is better in that range. We don't want to send high energetic X-rays to the tissue. Another system is called fluoroscopy, which is also utilizing X-rays. There are 2 pictures on the slide. The picture on the left side is the instrument or the imaging system is used in a real operation. You see the doctors at the right side of the photo, and at the left side, there's a so-called C arm, because letter C, ABC, is the shape of the arm, and upper side, there's digital detector, and at the lower side, there's a tube, X-ray tube. This structure is called C-arm. It can be rotated in many degrees for suitable imaging needs. Also, now we come to a final application of X-ray. X-ray is also utilized in tomographic methods. Tomographic means slice imaging, and it's involving computerized processing as well as matrix solutions with iterative calculations after imaging data have been collected at the detectors and sent to the computers to be processed. These computers are basically creating the image that's being performed or obtained, okay? So in short, X-ray tomographic systems are called CTs, computerized tomography systems. Actually, their mathematics are more than 100 years old, but their clinical applications are, let's say, in the last 40, 50 years. They have developed in the last 40, 50 years. Here's a picture of a typical X-ray tomography system where it has, of course, a patient bed. The patient lies down, and this bed is upwards or downwards, left or right, can be moved by the operator next to the patient. And so-called a bore or gantry of the system, X-rays indicated with the red arrows are sent to the patient, and they are detected, and tube and the detectors are rotating in the gantry, and they are detected by the special detectors, usually solid state, by solid state electronic methods. And all the data, which an immense number of data, are sent to the computer to process the X-ray CT data. A simplified version of data collection and reconstruction goes back to the 1970s in the first early ages, where to the left side, the patient, you see the cross-section of the patient and the gantry or bore of the system, and the source and detectors, where you see the X-ray beam through the patient, are rotated around the patient, and they have so-called a kind of projection data, where this is the graph of the signal obtained in each detector. The detector is a kind of angular arc, okay, where small pixels are located, and their charge intensity values can be converted to voltage for a projection characteristics. By rotating the source and detector, you obtain another projection, and you complete the circle from 360 degrees. You obtain as at least 360 or even more projection data, and these data are converted to image format, so-called filtered back projection and other mathematical radon transform kind of mathematical methods, which is not the scope of this course, which is an advanced topic for medical imaging, probably graduate course level. So by using this matrix algebra and computerized methods, the image is obtained at the right side, as you see. Today, one more step was obtained to obtain so-called helical computerized tomography systems. So not only 360 or one revolution data collection, rather a volumetric, okay? You see, that's a kind of spiral movement, spiral, helical. So volume imaging can be obtained by this method, and in these kind of systems, source and detector are continuously rotating. The source is not continuously sending or emitting X-rays. As soon as the operator hits the button, in a few revolutions, complete volumetric image is obtained, and this is again a very heavy or mathematically dense method. So this is like a description from a book related to spiral or helical computed tomography systems. Another system also appears in today's hospitals. This is called, it's a CT, but it has two different energetic X-rays sent to the patient. Where you see on the left side of the image, there are two tubes. Tube 1 sends the X-ray in energy 1 bandwidth, and tube 2 sends the X-ray in energy 2 bandwidth. What's the advantage of this? Some tissues have good contrast at some energy levels, but other tissues at energy 2. So if you want to see the tissues on the same graph, on the same image, sending single energy may not show the other tissue well. So two different energies may yield a kind of image fusion, image combining, or getting the best outcome for two different kinds of tissues, like the one on the seen on the right side, as blood vessels and some organs cannot be simultaneously seen at one energy level, but they can be seen in two different energy levels with better contrast. Now we have to mention a very important parameter of computed tomography. This is called CT number, because in mathematical operations in the computer of an imaging system, not X-ray absorbance coefficient units like 1/centimeter, etc. are used. Rather, a kind of referenced integer number called CT number is used. That CT number is a kind of normalization of the X-ray absorption compared to the water, okay? So CT number formula is a very easy formula. There's a constant times a difference in X-ray absorption coefficients denoted by Greek letter mu over the X-ray coefficient of water. Usually K is 500 to 1000 in that book. Okay, that book was very old, like 40 years or so. Today, K is always assumed to be 1000. Okay, so it's like the difference of any tissue compared to the water's X-ray absorbance, and it's normalized with the water X-ray absorbance value. This is called a CT number. And if we'll have an examination, definitely there will be a question related to that CT number calculation. So once again, emphasizing this, CT number equals to 1000 to difference of X-ray absorbance values of the unknown tissue with water, normalized with the water. CT numbers, according to this table given in that reference, are or can be stated as C. You see very X-ray opaque or X-ray absorbance high tissues do have very large numbers of CT, like bone, etc. And air, which is on the 5th row, is almost, it does not attenuate X-ray, so it's completely below, so that's minus 1000. Water, as from the formula indicates, it has 0, so that's a kind of reference. The other tissues are, you see, in between 10s or 30s or 45s, etc. And these number creates the X-ray contrast. Let's have a very little basic introduction to the mathematical operations, because computerized tomograph systems utilize these mathematical operations. And what kind of operations do they involve? Of course, those are matrix operations. For example, think of a very simple image, 2 by 2 pixels, okay, 4 unknowns at the center. Consider that's our object. Our object is circular. We have 4 unknowns to determine. So we send the X-ray from the tube to the detector from left side to the right side. We obtain 2 intensity values, I1 and I2. So we have 2 equations, but we have 4. Since we have 4 unknowns, we have to repeat this experiment in another angle to have at least 2 more equations, which is from the top to the bottom. We obtain I3 to I4. So at least, so that's enough for us theoretically, mathematically, to solve that system equations. But in practice, due to electronic and other physical noises, the number of measurements are always more than the number of unknowns and in order to maximize signal to noise ratio. Nevertheless, let's focus on our very simple case. Our equations are on the form of intensity I equals to some incident intensity times some exponential values. Those exponential values include the X-ray absorbance of at least two different pixels shown with mu sub jk plus mu sub mn. And I here is changing from 1 to 4 because we have 4 unknowns or pixel values. And by rearranging this equation, we obtain a kind of measurement I in the last row, measurement I equals to 1 or delta x. Delta x is arbitrarily determined as the dimension of a pixel. So it's known beforehand, okay? I0 in the ln part, I0 is also known because that's the intensity of the incident ray. And I sub I is measured at the detector side. So this measurement gives the sum of two unknowns, mu sub xk, jk and mu sub mn. If we repeat everything to all pixels, we have 4 equations in a similar form with 4 unknowns. We can consider this or transform it a matrix equation as shown. So these matrix unknowns can be calculated by utilizing matrix algebra in the last row at the right side, where the vector mu, which is unknown vector, equals to the inverse of A. A is the 4 by 4 matrix. You see, A is a big matrix because 4 unknowns, we have 4 by 4 matrix. For realistic cases, in the clinical environment, 512 to 512 is a typical image size. So its matrix is at least 512 by 512, which is usually not the case. Those systems collect more data than the unknowns. So in these equipments where the engineers are interested in, during the first installation of the system, the computerized tomograph system, and in routine periodical maintenance procedures, calibration is performed. Calibration determines the incident X-ray exposure intensity, detector gains, etc. Then, according to the angles and position and partially illuminating the pixels by X-ray, the weightings in A matrix can be also determined, and these are done in the calibration processes. So if the system of equations or the object increases than our basic primitive 4-pixel thing, you see, I need more angular X-rays, and at this time, some angles partially enter any pixel, like shown that oblique line, then we should add a kind of weighting factor, and these factors are all seen in that big A matrix in the computerized tomography system. So, in summary, an CT image, computerized tomography image, is a grayscale image, shows the X-ray attenuation coefficients or mu's, but really Hounsfield units. Okay, so in the computer disk or storage media, so-called raw data contains only HU numbers, Hounsfield numbers. Those numbers are shown with grayscale. Related to these kind of systems, we have also, we should also mention patient safety. Once again, you remember in the first and second week, I mentioned non-ionizing and ionizing radiation. In X-rays, and also I had defined exposure and dose of a patient. So these are the typical doses utilized in clinical environments, and effective dose are given in millisieverts. We have also, nowadays, we also have dual systems containing both computerized tomography as well as another system called single photon emission computed tomography, which also we will use in nuclear medicine systems. So this is like a combination of two different imaging systems. These also occur in the imaging world, but we will mostly deal with it after we see the nuclear imaging courses. So thanks for listening and retrieving week number 4. I will proceed with the week number 5 by taking or thanking to these files. Now I'm continuing with the 5th week. So this is the week before our outbreak holiday. Okay. So let me share. Week number 5 with you guys. In a few moments, you'll be observing it. Can I have your feedback? Did you understand my week number 4 explanation? Everything's okay? Technically, what do you think? Nobody answered me.
Her şey çok iyiydi hocam. Teşekkür ederiz.
Bir şey değil. Arada bir geri bildirim verin. Böyle ekrana boşa konuşmak kayıp oluyor.
Hocam arkadaşlar chat'e yazdılar.
Chat'e mi yazdılar? Bakayım.
Evet hocam.
Pardon.
Hocam
Söyle.
sesim geliyor mu?
Geliyor.
Slide üzerindeki resimlerden anlatırken fareyi kullansanız daha iyi olabileceğini düşünüyorum ama.
Neyi kullanayım?
Yani imleci kullansanız hani nereyi kastediyorsunuz tam olarak? İşte açı falan diyorsunuz ya mesela.
Anladım. Şöyle yapalım. Şimdi imleci görebiliyor musunuz?
Evet hocam.
Evet hocam görebiliyorum.
Evet hocam.
Oo, çok güzel. Anlaşıldı.
Gözüküyor.
Süper. Okay, let's continue. Week number 5, which is a kind of collection of X-ray systems which can be found in today's clinical environments. So this is the first kind, which is a conventional X-ray system. It's called table X-ray system. Patient lies down here and X-ray tube is there. It can be adjusted to anywhere. And the detector or the film, previously film, now a digital detector is underneath the table. So the patient lies down, X-ray is from top to bottom, illuminates the detector for imaging. If the patient is not lying but standing, then the patient stands here, the tube is rotated 90 degrees, and this is the detector or filming environment for usually thorax imaging. There probably you all guys know these are experienced these kind of systems. This is another kind of a conventional table X-ray system with a little bit more mechanical accessories. Let's say it can move from the ceiling with a wider area, etc. So these can also be found in the clinical environment. For example, this one has been found from internet, has a capacity of maximum voltage of 150 kilovolts and milliampere range of 0.5 to 800 milliamp seconds. You remember, this is the anode to cathode voltage to accelerate electrons. This is the amount of current through the filament and determines the number of electrons free from the filament, because you remember, free electrons when attracted to anode creates X-ray photons. So the larger of this number gives the larger number of X-ray photons at the end. The larger number of this kilowatt value determines the maximum energy that a photon can carry. So they are the two very important parameters of X-ray systems. The other parameters also exist about some kind of detector, let's say, options. Their size, pixel size, resolution values are shown with different options commercially available with that system. I will not mention the brand name, but mention technical details. So basically, that's the table X-ray assembly. X-ray systems can also be mobile, so-called mobile systems. So this is, you see, a mobile system with wheels. So this is the X-ray tube, this is the monitor, and the computer and other hardware are in it with the box. One or two people can carry this even to the patient bed. So this is a mobile X-ray system. The principle is the same, only it's very compact with less abilities than other table X-ray or X-ray systems. This is another example of an instrument found in the clinical environment. It's a mammography system. Again, the tube and detector are in a very, let's say, compact and small nature for tissue breast imaging examinations. So this is a typical tomography system can be found in the hospitals. It has special room and console. Usually console is not next to the machine, but rather it's in a separate room. That room is shielded to avoid the X-rays. And this is another type of tomographic system. And this is all about it related to week number 5.